A perfect line cuts across an empty desert, laid down millennia before the first satellite. This video reveals exactly how ancient surveyors created straight roads without a single modern instrument. You will learn the forgotten methods that let empires impose their will on the landscape itself. How did they align a road for hundreds of miles using only the stars and simple stakes? And what ingenious device became the Roman Empire's secret weapon for precision? What does it say about us that our oldest roads still point the way forward? That straight line across the map was a declaration of intent. It announced that a distant capital's will could be felt instantly, anywhere within its reach. To understand why ancient engineers obsessed over perfect alignments, we must look beyond simple convenience. These roads were the very foundation of imperial power. In a world without radio or telegraph, the speed of a marching legion or a royal messenger was the ultimate measure of control. A winding, meandering path might add days or even weeks to a critical journey. In times of conflict, that delay could mean the loss of a frontier province or the failure to quell a rebellion before it spread. So the drive for straight roads was not about aesthetics. It was a matter of survival for the state itself. Think of it as the ancient world's high-speed data network. Just as today we rely on instant communication to manage global systems, empires relied on the physical movement of people and goods to bind their territories together. A straight road enabled efficient trade, which filled the imperial coffers. It allowed census takers and tax collectors to travel further, faster, bringing more of the realm under direct administrative oversight. Most crucially, it meant that the symbol of imperial authority, the soldier, could appear with shocking speed to enforce the peace or project power. This strategic imperative created an enormous demand for precision. You could not govern a continent with guesswork. The need for reliable, repeatable surveying methods was born from this simple, brutal reality. The stability of an empire, its economic growth, and its very unity were paved one straight, meticulously measured mile at a time. This overwhelming need is what pushed ancient minds to look to the heavens and the horizon, searching for the tools to draw their lines of power upon the earth itself. The sky itself offered the first and most reliable map. Before any road could be sketched upon the ground, its direction had to be anchored to something unchanging, something beyond the hills and forests that could deceive the eye. Ancient surveyors turned to the only reference frame they knew would never shift with the seasons or the whims of rulers, the celestial compass of the sun, moon, and stars. In the northern hemisphere, the North Star, Polaris, became a fixed point of light around which the entire heavens appeared to slowly turn. By sighting on this steady beacon, a surveyor could determine true north with remarkable accuracy. In southern latitudes where Polaris dipped below the horizon, other constellations like the Southern Cross served a similar navigational purpose. This was not just stargazing, it was high-precision orientation. The process often began with something as humble as a single vertical stake driven into the earth, a gnomon. As the sun journeyed across the sky, the shadow of this stake would trace a perfect arc. The surveyor would mark the tip of that shadow at different points in the morning and afternoon. A line drawn between those two marked points would run perfectly east to west. Bisecting that line gave them a true north-south axis. With that, they had done something profound. They had captured a slice of the cosmos and pinned it to the ground, creating a sacred baseline from which all earthly measurements would flow. This celestial alignment was the master key. Every subsequent measurement, every right angle turned, every mile counted, would refer back to this line drawn from the heavens. It meant that a road begun in one province would point in precisely the same direction as a road begun 1,000 miles away, because both were aligned to the same infinite reference. Their earthly endeavors were literally written in the stars, a testament to a worldview that saw human order as a reflection of cosmic order. but a line drawn in the dirt is a fragile thing. But a celestial line is an idea, not yet a road. To carve that perfect geometry into the living earth, the Romans relied on a deceptively simple tool that became the backbone of their empire, the Groma. Picture a portable altar to precision, a cross made of wood or bronze mounted on a sturdy staff. From the end of each of its 4 arms dangled a simple plumb bob, a weight on a string. This was not high technology by our standards, but in the hands of a trained surveyor, it was a machine for creating order. The principle was elegant. By aligning 2 opposite pairs of these hanging strings with a distant sighting pole, a surveyor could establish a perfectly straight visual line. But the Groma's true genius was in its ability to create perfect right angles, the essential building block of Roman planning. Once the main road's line was set using the celestial methods, the Groma would be set up directly over a marker stake. The surveyor would then rotate the device until one pair of plumb lines aligned with the existing road. The other pair, now hanging at a 90-degree angle to the first, would point the way for a perfectly perpendicular side road, a drainage ditch, or the boundary of a military camp. This was how the relentless grid of Roman civilization was stamped across continents, one right angle at a time. The process, however, was anything but easy. Using a Groma required the patience of a monk and the steady hand of a surgeon. A gentle breeze could set the plumb bob swinging, turning those crisp lines into blurry, useless arcs. Surveyors would often work at dawn when the air was still, or even use simple windbreaks. They had to account for the sag in the strings, the levelness of the ground, and the human eye's tendency to err. It was a dance between immutable mathematics and a frustratingly physical world. This tool, more than any grand monument, embodies the Roman ethos. It was not about flashy invention, but about the systematic, repeatable application of a brilliant idea. The Groma made precision democratic, a process that could be taught, replicated, and trusted from the hills of Scotland to the deserts of Syria. Every straight Roman road, every rectangular field parcel, every orderly city block whispers the name of this humble instrument. It translated the abstract lines of the sky into the tangible reality of stone and soil, proving that empire is built not just on the might of legions, but on the unwavering certainty of a right angle. Yet the Groma had its limits. Over vast distances, across hills and valleys where direct sight was impossible, the Romans and countless other ancient cultures employed a method of breathtaking simplicity. Their most reliable tool was not made of bronze or wood, but of disciplined observation and coordinated human effort. This was the principle of aligned sight poles, a technique so fundamental it remains at the heart of surveying to this day. The process began with a clear directive from the lead surveyor. Teams would venture into the landscape carrying tall, slender poles. These were often whitewashed to stand out against the green of forests or the brown of plains, or topped with bright flags that could catch the eye over long distances. The lead surveyor would stand firmly at a starting stake, his back to the established line. An assistant would then walk forward, perhaps a few hundred paces, and plant a pole into the ground. From his fixed position, the surveyor would look past the first pole, squinting into the distance. With hand signals or shouted commands, he would direct the assistant to move the pole left or right, sometimes just an inch at a time, until it disappeared from view, perfectly hidden behind the pole at his own station. In that moment, when the 2 poles became one in his line of sight, he had established a flawless straight line. But this was just the first link in a chain. The assistant would then become the new anchor. He would hold his position while a second assistant moved further ahead to plant a third pole, aligning it with the second. The lead surveyor would then walk forward to the second pole, confirm the alignment, and the leapfrog process would continue. Step by step, team by team, they would march that straight line over the horizon, conquering rolling hills by simply ensuring each new marker was invisible behind the last. This method, called ranging or lining in, required immense patience and trust. It turned surveying into a symphony of clear communication and shared visual focus. A gust of wind, a misheard command, or a moment of fatigue could introduce a tiny error that, compounded over miles, could bend the entire road off course. It was a testament to the power of the human eye, calibrated by geometry and amplified by teamwork. They proved that precision was not solely the domain of complex machinery, but could be achieved through rigorous process and collective attention. Every straight Roman road that crests a hill and continues unerringly into the valley beyond is a monument to that moment of alignment, to the shouted command across a windy field that said, "Move it a little to the left until you disappear." But a road that is perfectly straight can still be a failure if it becomes a river of mud with every rain. The ancient surveyor's final, and perhaps most subtle, challenge was not just drawing a line, but giving it a gentle, consistent slope. They needed to master the third dimension, ensuring their majestic avenues would drain properly and stand the test of time. For this, they turned to one of nature's most reliable guides, water itself, which always seeks its own level. The most sophisticated Roman answer to this problem was a device called the chorobates. Imagine a wooden bench as long as two men, with a precise groove carved along its top. This trough would be filled with water, and the surveyor would patiently wait for the surface to grow perfectly still. When the water rested at precisely the same height against markings at both ends of the groove, the entire frame was confirmed to be level. It was an elegant application of a fundamental law of physics, transforming a simple observation into a tool of empire. With the chorobates set up at one point, surveyors could then measure how much higher or lower the next point was by using graduated rods, calculating the exact gradient they needed to achieve. This allowed them to plan a road with a nearly imperceptible slope, often as little as 1 part in 100, just enough for rainwater to run off into side ditches without eroding the precious surface. In areas where such precision instruments were unavailable, simpler methods prevailed. Teams might dig a long, shallow trench and fill it with water, using the calm surface as a continuous reference line across uneven ground. Or they used the principle of connected vessels, understanding that water in 2 pots linked by a hose would always settle at the same height, allowing them to compare elevations over surprising distances. This relentless focus on grading was what separated a permanent imperial highway from a mere dirt track. A well-graded road would not wash out in a storm. It would allow carts to roll with less effort, whether going uphill or down. It meant that the vital flow of soldiers and messengers could continue through the autumn rains and the spring thaws. The straight line guaranteed the shortest distance, but the carefully calculated slope guaranteed that the road would remain open, turning a seasonal path into a perennial artery of power. This marriage of alignment and gradient represents the full genius of ancient engineering. It was not enough to see the destination on the horizon. They had to feel the very texture of the land underfoot to persuade gravity itself to work for them, ensuring that every mile they paved was a promise meant to last for centuries. Even the most determined straight line eventually meets an immovable object, a sheer cliff face, a deep lake, or a sacred grove that cannot be cleared, would seem to force a road to bend, to surrender its geometric purity to the messy reality of the land. Yet ancient engineers refused to accept this compromise. Their solution reveals a leap from practical measurement into the realm of pure abstract thought, a secret weapon for conquering distance without ever touching it: triangulation. The principle is elegant in its logic. Imagine you need to know the distance across a wide river to continue your road directly opposite your current position. You cannot simply stretch a rope across the water. Instead, you start by creating a baseline on your own side of the obstacle. This is a line of perfectly known length, measured with painstaking care using rods or chains. You mark one end point A and the other point B. Now, from point A, you sight the exact tree or rock on the far shore where you wish your road to emerge, point C. You carefully measure the angle between your baseline and the line of sight to point C. Then you walk to point B and repeat the process, measuring the different angle from this new position to that same distant point C. You now have a triangle. You know the length of one side, your baseline, and you know the two angles adjacent to it. With this information, the laws of geometry reveal everything else. The precise distance across the river and the exact direction to resume your straight line are now solvable numbers, emerging from the relationship between those angles and that one known length. This was trigonometry in action, a conceptual toolkit understood by Greek, Indian, and Chinese scholars and applied by Roman surveyors in the field. It meant an obstacle was no longer a barrier but merely a geometric puzzle. They could walk around a hill measuring angles as they went and calculate exactly where to pick up their original alignment on the other side, as if the hill were not even there. The straight line in their minds never broke. It simply passed through a mathematical space they could navigate around. This application is profoundly revealing. It shows that these builders were not just following rote procedures. They were thinking in shapes and relationships, using an invisible framework of triangles to overlay the visible world. A cliff was not just a wall of rock, it was a problem of angles. A lake was not an interruption, but a gap in a diagram they could complete with calculation. This abstract thinking allowed their roads to exhibit a kind of intellectual stubbornness, a refusal to let the physical landscape dictate terms. The road's destiny, set by the stars and the Groma, would be fulfilled, even if the path to get there required a temporary detour through the elegant world of triangles. It was the ultimate fusion of mind and matter, proving that the straightest path forward sometimes requires first taking a step to the side to measure the angles. A line of sight and a right angle are still just ideas without a number attached to them. To translate vision into a built reality, ancient surveyors needed to answer the most fundamental question of all: how far? Their solution was a triumph of organization over brute force, a rhythmic, physical process that turned individual effort into a collective measurement of staggering accuracy. This was the human chain, a relay race of distance that stretched across continents. At its heart was the need for a universal language, a standardized unit that meant the same thing on a dusty plain in Gaul as it did in a sun-baked outpost in North Africa. For the Romans, this was the actus, a length of 120 Roman feet. But a standard is useless without a tool to enforce it. Surveyors carried these units into the field as physical objects, knotted ropes stretched taut between stakes, carefully calibrated wooden rods, or for the most important imperial projects, chains made of identical metal links. Each link, each knot, each marked section on a rod was a promise of consistency. A team would begin at a marker stake, the end of their last celestial alignment. Two men would take the ends of a measuring rope, perhaps one actus in length, and pull it perfectly taut along the sightline established by the distant poles. A third would then drive a new stake into the ground at the rope's far end. This was the first unit. Then the rhythm began. The team would pick up their rope, walk past the new stake, and repeat the process. The man at the rear would become the new anchor, holding his end precisely at the last stake, while his partner walked forward, pulling the rope straight once more. Over and over, this human machine would advance, laying down the empire one measured segment at a time. The physicality of this work cannot be overstated. It was a battle against the landscape itself. A gentle slope could cause the rope to sag if not held level. A gust of wind could blow it offline. The ground might be rocky, hard, or uneven, making it difficult to plant a stake exactly where the rope ended. The precision of the final road, over hundreds of miles, depended entirely on the care taken in each of these thousands of repetitions. A tiny error, a rope held slightly slack, or a stake placed a hand's width off the mark, would be compounded with every new segment. What began as a minor mistake at sunrise could, by sunset, mean the road was drifting dozens of feet off its intended path. This is why surveying was a profession of immense discipline and trust. It was a silent contract between team members, a shared understanding that the integrity of the entire empire's network rested on their collective focus in that moment, on the tautness of a rope and the true placement of a simple wooden stake. They were not just measuring distance, they were weaving the very fabric of imperial space, stitch by meticulous stitch, transforming the abstract actus into a tangible line of communication that would endure for millennia. The straight road, therefore, was never a single act of genius, but the accumulated product of countless ordinary acts of exactitude. The true test of a surveyor's line was not the open plain, but the moment it met a wall of trees. A forest presented a unique kind of blindness, swallowing sight poles and celestial alignments into a shadowy, tangled chaos. Here, the ideal of straightness clashed directly with the physical world, and the response was one of brute, determined clarity. Teams would advance into the woods, axes in hand, not to clear the entire roadbed, but to carve a single, slender corridor of visibility. This was a surgical cut, just wide enough for a surveyor to stand at one end and see his distant marker at the other. It was a declaration of intent, a line of light forced through the darkness, proving that the human will to connect could not be thwarted by mere density. Every felled tree along that sightline was a measured step in the conquest of distance, transforming an impenetrable barrier into a temporary inconvenience. The straight road would pass because the surveyors first made a space for it to be seen. Water presented a different puzzle altogether, one of precision deferred. A wide, flowing river could not be bullied into submission with an axe. Here, the strategy shifted from force to foresight. Before a single stone was laid for a bridge, the surveyor's work was absolutely critical. Using their methods of triangulation from the safe, solid bank, they would determine the exact point where the road should meet the water on their side, and the exact point where it should resume its journey on the far shore. They would drive massive, unmistakable marker posts deep into the earth at both locations. These posts were not just for them, they were a message to the engineers and stone masons who would follow. They said, here is where the bridge must begin, and here is where it must end, so that the road's sacred alignment is preserved across the void. The bridge itself, a marvel of engineering, was in service to this earlier, quieter act of measurement. It was built to fulfill a promise made by surveyors standing on dry land, staring across a torrent, trusting completely in the angles they had drawn and the numbers they had calculated. But perhaps the most awe-inspiring adaptations occurred where the land rose violently toward the sky. In mountainous regions, the dogma of straightness had to be reinterpreted with brilliant flexibility. A road could not simply charge up a sheer cliff. Instead, surveyors and engineers collaborated on designs that served the spirit of the direct route, if not its letter. One widespread solution was the switchback, a series of zigzagging ramps that climbed a steep slope like a carefully folded ribbon. From a distance, the overall path of the road remained direct, aiming unerringly for the pass or the plateau. But up close, it accommodated the impossible grade with a repetitive, manageable rhythm. This technique is masterfully displayed in the roads of the Inca Empire, where stone-paved switchbacks cling to Andean precipices, maintaining a functional gradient for travelers and llama caravans. In other cases, when a ridge stood as an absolute barrier, the solution was to go through it. Tunneling, an immense undertaking with ancient tools, was the ultimate expression of tenacity. It was a statement that no amount of rock would divert the empire's predetermined path. The decision to go over, around, or through an obstacle was never casual. It was a profound calculation, weighing the immense labor and resources required against the eternal value of a permanent, reliable route. They understood that a road that washed away on a hillside or that forced travelers into an exhausting detour was a broken promise. So they bent their methods but never their ultimate purpose. The line on the map might develop a graceful curve or a patient series of angles, but its destination never wavered. This pragmatic genius ensured that the network of civilization did not merely connect easy places, but bound together entire landscapes, transforming mountains from barriers into waypoints in an endless, deliberate journey. The principles we have explored were not just theory, they were forged in stone and mortar on roads that reshaped the world. Perhaps no single path better embodies this marriage of ambition and technique than the Via Appia, the Appian Way. Begun in the year 312 before the Common Era, this was Rome's first great military highway, a direct line of conquest and control stretching from the city gates toward the distant south. Its most legendary section cuts a ruler-straight path across the treacherous Pontine marshes, a landscape of water and soft earth that defied any ordinary construction. Here, the surveyor's craft faced its ultimate practical test. Before a single slab of basalt could be laid, teams had to conquer the marsh itself. Using their Groma to establish a flawless alignment, they then orchestrated a monumental feat of civil engineering. They dug parallel drainage ditches on either side of the planned route, channeling the standing water away and slowly exposing the firmer ground beneath. This was not merely building a road, it was creating the very land upon which the road would stand. The straight line across the marshes was therefore a double victory, a triumph of precise measurement over direction and a triumph of organized labor over geology. The resulting roadway, built with layered stone and sealed with tight-fitting polygonal blocks, was so solid, so deliberately imposing, that it became far more than a transport route. It was a physical manifesto. Every mile of its unwavering trajectory shouted a message to citizens and rivals alike, that Roman order could not be swayed by nature, distance, or time. This road directed the flow of history for centuries, carrying legions to expand the empire, facilitating trade that enriched it, and even serving as the setting for pivotal events, like the aftermath of the Spartacus rebellion. The Appian Way demonstrates that ancient surveying was never just about drawing lines. It was the essential first step in a process that fused political will, brutal manpower, and refined technique to create permanent monuments. The road did not adapt to the landscape, it commanded the landscape to adapt to Rome's vision. When you stand on those ancient stones today and look down that seemingly endless straight corridor, you are not just seeing a path, you are reading the opening sentence of an empire's story, written not on parchment but directly upon the earth. Yet while Roman roads proclaimed dominion over the marsh, another empire was threading straight lines through the clouds. High in the Andes, the Inca built a network of roads so vast and precise it formed the backbone of the largest empire in the pre-Columbian Americas. Their achievement presents a fascinating counterpoint, a testament to how the same principle of straightness can be reinvented by a different culture facing an utterly different world. Without the wheel, without iron tools, and without the Groma's plumb lines, the Inca surveyors looked to the mountains themselves for their guides. They used natural landmarks, distant peaks that held spiritual significance as eternal sighting points. To establish a line across a dizzying valley, they might light signal fires on opposing ridges, using the smoke to visually connect 2 points in a straight line across the empty air. For the critical task of grading, they likely employed a beautifully simple tool called a weira, a wooden frame with a hanging stone plumb bob. When the plumb line hung directly over a mark on the crossbar, the 2 feet of the frame were level. By walking this device forward in a careful chain, they could trace a consistent, gentle slope up the most severe inclines, ensuring their paths were walkable. This adaptation to vertical terrain produced roads of breathtaking audacity. Where a Roman road would switch back, an Inca road often went straight up, transforming into a flawless stone staircase carved into a cliff face. These were not roads for chariots or carts, but for foot traffic and sure-footed llama caravans. The straightness served efficiency, yes, allowing messengers or chasquis to run at speed along relay routes, but it served a deeper purpose as well. The roads were woven into the sacred geography of the Andes, connecting temples, shrines, and ceremonial centers in lines that resonated with spiritual meaning. The long, straight stretches across high plains were not just practical, they were ceremonial avenues integrating the movement of people and goods into the ritual order of the universe. Placing the Inca system beside the Roman reveals a profound truth. The drive to create straight paths for control and connection is not the property of any one technology or culture. It is a human response to the challenge of governing space. Rome used celestial alignment and the Groma to impose a grid on a horizontal world. The Inca used mountain peaks and the Wira to integrate movement into a vertical, sacred landscape. Both arrived at the same elegant solution, the shortest, most controllable distance between 2 points, through completely different tools and philosophies. This independent emergence of the idea speaks to something universal in our relationship with the land. It tells us that when a society reaches a certain scale and ambition, it looks at the winding, chaotic paths of nature and feels a deep need to draw its own line, a statement of order, purpose, and connection that says we are here and we are linked. A straight line drawn in the dirt is a fleeting thing, vulnerable to rain and memory. The true permanence of these ancient roads came not from the stone, but from the mind. Behind every Groma and every sighting pole stood a sophisticated intellectual framework, a system of mathematics and meticulous record-keeping that transformed a local construction project into a repeatable, scalable empire. The Romans, masters of this approach, did not just send out laborers with tools. They sent out the Agrimensors, the land surveyors, who were as much scholars and legal experts as they were engineers. These men were formally trained in geometry, the science of shapes and spaces, and in the laws of property and public works. Their job was not merely to measure, but to know, to document, and to create a lasting legal truth from the lines they drew. This intellectual discipline was the invisible bedrock upon which the physical road was built. After a team had painstakingly ranged a line across miles of countryside, the work of the Agrimensor was just beginning. He would compile everything into a formal record: distances between markers, the angles of turns, the names of neighboring landowners, and descriptions of permanent landmarks, a distinctive tree, a large rock, a spring. These records were not scribbled on perishable parchment. For the most important boundaries and roads, they were often inscribed onto durable bronze tablets or carefully entered into codices, the early form of bound books. Think of these as the ancient world's technical blueprints and legal deeds, fused into one authoritative document. This bureaucracy served a profound purpose. It made knowledge transferable. A surveyor in Britain falling ill or completing his service could hand his records to a replacement who, by reading the precise measurements and landmark descriptions, could immediately understand the exact alignment and status of the road. This meant a project could span generations of workers without losing its original intent. More importantly, it allowed for maintenance and replication. If a section of the Via Appia was damaged by a flood, officials in Rome could consult the central records to know its exact original width, gradient, and construction specifications, so it could be repaired correctly. If a new province needed a road system, they could send teams trained in the same methods, using the same units of measurement, to replicate the system elsewhere. The mathematics provided the logic, the geometry of triangles and right angles, but the record-keeping provided the memory. It was this combination that elevated infrastructure from a one-time achievement into a perpetual system. The straight road, therefore, was not just a feat of engineering, it was a triumph of information management. It proved that to control a vast territory, you needed more than armies, you needed archives. You needed the certainty that came from a number written down, a boundary described without ambiguity, a line that could be defended in a court of law as easily as it was defended on the frontier. The physical road asserted power over space, but the records on those bronze tablets asserted power over time itself, ensuring that the empire's will, encoded in measurements and landmarks, would outlast the individuals who first conceived it. The knowledge held by an Agrimensor was a form of power, and that power was far too valuable to be left to chance. Becoming a Roman surveyor was not a casual apprenticeship, it was a rigorous education that blended the mind of a mathematician with the eye of a farmer and the authority of a judge. This formal profession, often passed from father to son or taught in dedicated schools, produced the elite technicians who could translate imperial decrees into physical reality. Their training began with the abstract purity of geometry, mastering the theorems of Euclid not as academic exercises, but as essential tools for carving right angles out of wilderness and calculating distances across impassable rivers. They learned to handle the Groma with a surgeon's precision, to read the subtle swing of a plumb bob in a breeze, and to orchestrate the ranging of sight poles over miles of broken terrain. But geometry alone could not build an empire. The Agrimensor's education extended far beyond the field manual. They were deeply schooled in Roman law, particularly the complex statutes governing land ownership, inheritance, and public rights of way. Why was this legal knowledge so critical? Because a surveyor's line did not just define a road, it defined property, wealth, and civic order. When two landowners disputed a boundary, it was often the Agrimensor, with his maps and measurement records, who was called to adjudicate. His word, backed by geometry and documented evidence, could settle conflicts that might otherwise erupt into violence. His stake in the ground was not just a marker, it was a legal verdict rendered in wood and stone. This authority demanded more than technical skill, it demanded trust. To earn that trust, the trainee learned to read the living landscape with a profound, practical wisdom. He studied soil types, understanding which clay would hold a foundation and which sandy loam would wash away with the first storm. He learned to predict drainage patterns by observing the lay of the land after a rainfall, ensuring his roads would shed water and not become treacherous bogs. He could look at a hillside and visualize not just the straight line over it, but the engineered switchback that would make the climb sustainable for centuries. This unique fusion, this trinity of skill, made the Agrimensor a cornerstone of Roman civilization. He was the technocrat who could apply theoretical principles to the gloriously messy, unpredictable real world. A perfect alignment on papyrus meant nothing if the road built upon it flooded every spring or sparked a bitter feud between powerful families. The Agrimensor's expertise was the guarantee. It was the assurance that the emperor's straight line would not only be drawn, but would function, endure, and bring order rather than chaos. He stood at the crucial intersection where abstract law met physical earth, and with his calibrated chains and legal codices, he bound them together into the durable fabric of an empire. A road that never curves does something more than guide travelers. It reshapes how they see the world. The sheer visual dominance of a straight Roman road, slicing across meadows and over hills with geometric indifference, was a psychological weapon as much as an engineering one. For a citizen, stepping onto that paved surface was an act of submission to a larger order. Behind you lay the winding, unpredictable paths of the local village, governed by tradition and the lay of the land. Ahead stretched a line so deliberate it seemed to deny the very existence of hills and forests, a manifestation of a will that originated hundreds of miles away in the Senate or the emperor's court. This was not a suggestion, it was a command written in stone. Every mile you walked on it, you were reminded that your personal journey was now part of a vast, controlled system. The destination remained constantly in your sight, a point on the horizon that grew steadily nearer, creating a powerful sensation of security and measurable progress. You were not lost, you were on the grid. For a conquered subject, the message was even more stark. That road did not ask permission from the local spirits of the river or the ancient grove, it simply passed through them. Its construction often meant the clearing of sacred woods or the rerouting of ancestral streams, a literal paving over of the old gods in the name of a new, rational order from Rome. Traveling on it, perhaps under the watchful eyes of soldiers at a way station, was a daily lesson in where power now resided. The road said, "Our logic is stronger than your landscape, our time is more permanent than your traditions." This symbolic function was deeply intentional, a masterclass in using infrastructure as silent propaganda. Emperors understood that legitimacy was not just proclaimed in speeches or carved on triumphal arches, it was felt underfoot. A well-maintained, straight road radiating from the capital was a tangible promise of stability and good governance. It told people that the central authority could not only reach them, but could provide something of immense value, safety, and predictability in a dangerous world. It made the abstract concept of the state physically real, a constant companion on any long journey. In this way, the road became a political statement etched into the earth itself, reinforcing the idea of permanence. Rebellions might rise and fall, emperors could come and go, but the road remained, an enduring backbone of civilization that outlasted the individuals who built it. To walk its length was to participate in a ritual of belonging, to have your own story absorbed into the grand, straight narrative of empire. The empire's great stone arteries did not fall silent in a single day. Instead, they slowly faded like a heartbeat growing faint. With the gradual dissolution of centralized Roman authority in Western Europe, the sophisticated system that built and maintained those roads began to unravel. The Agrimensors, the master surveyors, found fewer patrons for their craft. Their meticulously kept records on bronze and parchment were scattered, lost, or simply no longer understood by the new powers emerging from the political fragmentation. The grand, interconnected network, which had required a continent-spanning bureaucracy to manage, began to suffer from 1,000 small neglects. A bridge here would collapse and not be rebuilt. A section of paving there would be quarried for local castle walls. The relentless, straight lines that had defied geography were slowly reclaimed by it, as tree roots cracked the stones and winter frosts heaved the foundations. Local paths, winding and pragmatic, continued to serve immediate communities, but the vision of a unified, measured space connecting distant provinces evaporated. The engineering precision for projects of imperial scale became a memory, a skill set without a society large or organized enough to require it. This was not a loss of the tools themselves, for the simple Groma or the principle of sighting poles had not been forgotten. It was a loss of the coordinated will, the vast resources, and the administrative genius necessary to deploy those tools across hundreds of miles. The capability shrank to the horizon of a local lord's domain. Remarkably, the flame of this knowledge was kept alive in quiet places. In secluded monastic scriptoria, monks copying ancient texts preserved the geometric principles of Euclid and the descriptions of Roman engineering methods. These manuscripts became treasure chests of a dormant science, waiting for a future that could read them with purpose. Meanwhile, in the East, the Byzantine Empire carried forward the Roman administrative and engineering tradition, maintaining vital roads and aqueducts and keeping the conceptual framework of large-scale public works alive within its own sphere. The contrast of this period is deeply revealing. It shows that technological capability is never just about having the right instruments or formulas. It is inextricably tied to the social and political organization that gives those ideas a canvas. The stones and the geometry remained, but the grand ambition that animated them had receded. The straight roads thus entered a new phase of their existence, no longer as active channels of power, but as majestic ruins. They became puzzling relics of a past order, their very straightness a haunting question mark across the landscape, challenging the fragmented world that now walked upon their broken surfaces. The broken roads themselves became a kind of text, waiting for a new generation of scholars to learn how to read them. Centuries after the last Agrimensor walked his line, a different kind of rediscovery began, not in the field, but in the quiet of libraries and the minds of Renaissance humanists. As Europe emerged from a period of fragmentation, there was a powerful yearning to reconnect with the sources of classical knowledge, to rebuild not just structures, but the very intellectual framework that had made them possible. This quest led scholars directly to the surviving manuscripts of ancient Rome, where they found the precise instructions they had been missing. The architect and polymath Leon Battista Alberti became a pivotal figure in this revival. He pored over Vitruvius's first-century treatise, De Architectura, a work that had survived the centuries largely intact. Within its pages, he found not just philosophical musings, but detailed, practical descriptions of the tools that had built an empire. Here was the chorobates, the water level, explained in clear terms. Here were discussions of the principles of sighting and alignment. For Alberti and his contemporaries, this was a revelation. It was not mere historical curiosity, it was a functional blueprint. They were facing their own monumental challenges, designing the ideal Renaissance city with its geometric piazzas and straight, imposing avenues, and constructing new forms of bastion fortifications to withstand cannon fire. These projects demanded a level of precision that medieval methods often struggled to provide. The ancient texts offered a solution, a lost science of measurement that was both rigorous and elegant. This relearning was an active, creative process. They did not simply copy the old methods, they adapted and improved them. Studying the description of the Groma, Renaissance instrument makers could reconstruct its principle, but they also began refining optical sighting devices, laying the groundwork for the theodolite. The chorobates inspired more portable and accurate spirit levels. This was the true power of the Renaissance rediscovery. It created a direct intellectual bridge. It allowed 15th-century engineers to stand on the shoulders of 1st-century agrimensors, to absorb their logic and then advance it. The straight line, as a concept of order and control, was reborn not as a ghost of empire, but as a tool for a new age of human ambition. The methods that had once served Caesar were now being studied to serve the vision of a Medici or the defense of a city-state, proving that the geometry of power is timeless, waiting only for the right minds to decipher its code once more. Rome's mastery was a brilliant chapter, not the entire book. Across the globe and across centuries, we find the same geometric will emerging independently, a testament to a shared human drive to bring order from chaos. In ancient Egypt, the processional avenues leading to massive temples like Karnak were not casually placed. They were deliberately aligned with celestial phenomena, often set to frame the rising sun on a significant festival day or to point toward a specific star. This was surveying in service of the sacred, a straight line connecting the realm of the pharaohs directly to the cycles of the cosmos. The precision required to extend these alignments over miles, using nothing but sighting poles and celestial observations, rivals the work of any Roman agrimensor, proving that the desire to anchor human construction to the infinite heavens was a universal engineering principle. Far to the east, in the fertile plains between the Tigris and Euphrates rivers, another civilization demonstrated its command over lines and levels. The Mesopotamians, masters of hydraulics, dug long, straight canals to irrigate their fields and control flooding. The success of these waterways depended on an almost imperceptible, consistent gradient. If the slope was too steep, the water would flow too fast, eroding the channels. If it was too shallow, the water would stagnate and silt up. Achieving this over vast distances using simple water levels and sighting methods represents a quiet, monumental triumph of early surveying. It was a geometry of survival, turning arid land into breadbaskets through the meticulous application of measured lines. In China, the impulse took the form of the cosmic grid. Ancient capital cities, most famously Chang'an, were laid out as perfect rectangles oriented to the cardinal directions, with broad, straight avenues dividing the city into orderly wards. This was not merely urban planning. It was a physical manifestation of a philosophical and spiritual worldview, where human society mirrored the perceived order of the universe. To establish such a perfect grid on a colossal scale required sophisticated techniques. Historical records and archaeological evidence suggest the use of sighting tools, calibrated measuring cords, and possibly even early forms of the magnetic compass for orientation. The Chinese surveyor, much like his Roman counterpart, was a technician of harmony, ensuring that the emperor's city was a precise echo of celestial law. These parallel stories from deserts, river valleys, and plains reveal something profound. The straight line is a recurring signature in the story of civilization. While separated by continents and cultures, Egyptian priests, Mesopotamian engineers, and Chinese planners all arrived at the same elegant conclusion. They looked at the untamed landscape and saw not an obstacle but a canvas. They understood that sight lines, water, simple plumb bobs, and the fixed points of the stars could be combined into a toolkit for transformation. This independent convergence on similar methods speaks to a deep-seated human logic. When a society reaches a certain level of complexity, the winding path of necessity is no longer enough. There emerges a compelling need to impose clarity, to create predictable, efficient, and symbolically powerful spaces. Whether for gods, for grain, or for governance, the straight line became the language of that ambition. A silent geometry written across the ancient world, each culture inscribing its own chapter in the same universal text. Yet the straight lines we admire from a map were never drawn by gods. They were laid down by human hands, working with imperfect tools in an unyielding world. This brings us to a crucial nuance: the limitations of ancient straightness. In our modern imagination, we picture these roads as laser lines across the continent, but the reality on the ground is far more revealing. The idea of straight was always relative. Over a distance of a few miles, the precision achieved with a Groma and sighting poles could be astonishing. But extend that process over 50 miles or 100, and the story changes. Every single measurement held the seed of a tiny error. A plumb bob might swing in a breeze just as it was sighted. A ranging pole might be planted a finger's width off the true mark. The ground itself might subtly shift over seasons. Each of these minuscule mistakes, when added together over thousands of repeated steps, would accumulate. The result was not a sudden, dramatic curve, but a gentle, almost imperceptible drift away from the original celestial alignment. This is not a failure of the engineers, it is the signature of reality. Archaeologists walking these ancient routes have made a fascinating discovery. Many of the most famously straight roads, when surveyed with modern instruments, reveal themselves not as single unbroken lines, but as a series of long, straight segments. These segments, perhaps several miles each, are joined by very slight bends or adjustments. Think of it not as a wandering path, but as a series of confident strides where the surveyor periodically stopped, re-established his bearings from a new fixed point, and set off again on a fresh, corrected alignment. These slight bends are the pragmatic fingerprints of the work. They might occur at a river crossing, where triangulation was used to resume the line on the far bank. They might appear where the road crested a high ridge, offering a new vantage point to sight a distant peak and correct any accumulated drift from the valley below. Sometimes the bend simply marks the point where one surveying team's section ended and another's began, each using slightly different local landmarks as their reference. This pragmatic approach shatters any illusion of cold, geometric perfection and replaces it with something far more impressive, a brilliant optimization. The goal was never a line that would satisfy a mathematician's theorem. The goal was the most direct practicable route, the line that balanced the ideal of straightness with the brute facts of watersheds, rock formations, and the limits of human endurance. They were optimizing for durability, for constructability, for maintainability. A road that insisted on going straight over a swamp would sink. A road that refused to bend for an outcrop of granite would require impossible labor. So they made the slight bend, accepting a minor deviation to ensure the road's ultimate survival and function. Understanding this subtle reality deepens our appreciation immensely. It moves the achievement from the realm of myth into the realm of human ingenuity. We are not looking at the work of infallible supermen, but of supremely skilled problem solvers who knew when to hold fast to their celestial line and when to let the land whisper a necessary correction. Their genius lay in knowing the difference, in weaving together intention, tool, and terrain into a pathway that served an empire for centuries. The true straightness of these roads was not in their unerring geometry, but in their unerring purpose. The gentle bends and weathered stones are a testament, but they are not the only evidence. To truly reconstruct the lost manual of the ancient surveyor, we must become detectives, piecing together clues from across the centuries. Our understanding is not drawn from a single source, but from a brilliant fusion of physical remains, recovered artifacts, and the precious words of the engineers themselves. This is a multidisciplinary puzzle where every fragment tells part of the story. First, we have the roads themselves, the most direct witnesses. Modern archaeologists no longer rely solely on walking the terrain. They now use technologies like LiDAR, a laser scanning system mounted on aircraft, to peer beneath dense forest canopies and see the ghostly imprint of ancient roadbeds invisible from the ground. These scans reveal the long, straight alignments with startling clarity, showing how the roads ignored minor contours and cut through obstacles, confirming the single-minded intent behind their construction. Ground surveys then follow, meticulously measuring the gradients, the widths, and those subtle bends, building a precise digital model of the engineering choices made 2,000 years ago. But the landscape only shows us the result. To understand the process, we need the tools. Remarkably, archaeologists have unearthed fragments of the technology. Parts of Groma have been found, their bronze arms and fittings silent until placed in context. Discoveries of standardized metal measuring rods and carefully knotted ropes provide the physical standards they used. A single recovered plumb bob is not just a weight, it is a key to understanding the swing and sway of their daily work, the tangible feel of precision in the hand. Perhaps the most vital clues come from the written word. We are fortunate that Roman administrators were meticulous record keepers. Figures like Sextus Julius Frontinus, who served as water commissioner for Rome, wrote detailed technical manuals. In his work on aqueducts, he describes the tools and methods for maintaining a consistent gradient over vast distances, offering a direct window into the surveyor's mindset. Then there are the boundary stones, the termini, often inscribed with the name of the overseeing official and the distance to the next marker. These are legal documents carved in stone, the permanent public record of a surveyor's line. All these sources provide the theory and the blueprint, but to answer the most practical questions, how accurate was a Groma in a crosswind? How fast could a team range a line? We turn to experimental archaeology. Here, researchers build and use exact replicas of the ancient tools. They take a reconstructed Groma into a field and try to lay out a straight line over a hill. They use replica measuring chains to see how much error creeps in over 1,000 paces. This hands-on testing is invaluable. It reveals the limitations that the written records gloss over, the frustration of a plumb line that will not settle, the physical challenge of holding a rope perfectly taut and level across uneven ground. Through this painstaking, multidisciplinary detective work, a remarkable picture solidifies. Each LiDAR scan, each rusted tool fragment, each line from frontinus, and each hour spent in a field with a replica Groma is a piece of the puzzle. Slowly, we are reassembling the lost training manual of the Agrimensor. This work does more than satisfy historical curiosity. It confirms a profound truth. It proves that the sophistication of these ancient methods was not in their complexity, but in their elegant application of simple principles. The evidence shows us they were not magicians, but masters of their craft, achieving a level of precision that commands respect across the millennia, written not in ink but in the very shape of the land. That pragmatic genius echoes in the hum of a laser on a construction site today. The conceptual bridge from those ancient sight lines to our modern blueprints is not a leap, but a direct, unbroken path. Every time a surveyor sets up a tripod-mounted theodolite, they are performing a ritual perfected by the Roman Agrimensor. The tool has transformed, swapping hanging plumb bobs for precision ground lenses and digital readouts, but its soul remains unchanged. It is still a device for creating perfect lines and measuring exact angles, for imposing human intention upon the raw geometry of the land. The fundamental process is eerily familiar. Before a single foundation is poured for a skyscraper, surveyors must establish a master baseline, a fixed reference line tied to permanent benchmarks. From this line, they use their instruments to turn perfect right angles, defining the footprint of the entire structure. This is not merely similar to the Roman method. It is the same method, refined by time but unchanged in its core logic. The Agrimensor, with his Groma planted over a marker stake, would watch this modern procedure and understand every step. He would nod in recognition at the careful sighting, the meticulous recording of measurements, the translation of abstract angles into physical stakes hammered into the ground. The language of the work has evolved from chains and actors to meters and digital point clouds, but the grammar of space remains identical. Even our most advanced techniques, like satellite-based GPS, fulfill the same ancient need the Groma once served, establishing a position relative to a fixed, reliable reference. Where the Romans used the North Star, we use a constellation of satellites, but the goal is the same: to know with certainty exactly where you are and exactly where you need to go. This continuity reveals a profound truth about human ingenuity. We have not replaced the old ways so much as we have amplified them, building layers of precision upon a foundation laid millennia ago. The straight line dreamed of by an Egyptian priest aligning a temple to the dawn sun, or by a Roman engineer plotting a road across a marsh, is the same line that guides a modern highway across a continent. It is a testament to the power of a simple, brilliant idea, that order can be drawn from chaos by measuring carefully, sighting truly, and thinking clearly. The legacy of these ancient surveyors is not buried in ruins. It is embedded in the very grid of our modern world, in every city block, every bridge, and every map that tells us with unwavering certainty the way forward. The undeniable precision of these ancient roads has, over time, inspired a persistent and popular modern myth. Some look at these straight lines stretching toward the horizon and whisper a tantalizing question: could this be the work of a lost, hyper-advanced civilization, or even visitors from beyond our world? It is a captivating story, but one that crumbles under the weight of the evidence we have just walked through. Every single feat of alignment and engineering we have explored has a perfectly human and perfectly logical explanation rooted in the tools and methods of the time. The celestial navigation that gave them true north, the humble Groma that carved perfect right angles from wood and string, the patient ranging of sight poles across miles of countryside. These were not gifts from the stars. They were the brilliant inventions of observant, determined minds working with the materials at hand. When you combine these tools with something the ancient world had in abundance, vast, coordinated human labor, the results are not mysterious, they are inevitable. The real magic was not in impossible technology, but in the sheer scale of the organization, the relentless will to see a project through for generations. To suggest otherwise, to credit these wonders to outside forces, does a profound disservice to the people who actually built them. It robs the Roman Agrimensor of his genius, the Inca stoneworker of her skill, and the countless unnamed laborers of their enduring legacy. The true wonder, the one that should take our breath away, is that ordinary human beings with eyes, hands, and minds not so different from our own, looked at a wilderness and conceived of a line. Then, with simple tools and immense patience, they drew that line upon the earth in stone, and it has lasted for 2,000 years. That is not a mystery to be solved by looking to the skies, but a triumph to be celebrated here on the ground, a testament to what we can achieve when we apply focused intellect to a shared, monumental task. A stone laid for progress often rested upon a foundation of profound hardship. The gleaming white roads that stitched empires together were not conjured from the earth by magic, but by the immense, sustained effort of countless individuals whose names history rarely recorded. This labor force was the true engine of imperial construction, drawn from the ranks of professional soldiers during peacetime, from enslaved populations captured in war, and from local communities conscripted into service through tribute or taxation. For these workers, the straight line was not a symbol of order, but a daily reality of backbreaking toil, carving through rock, moving mountains of earth, and fitting massive stones under a relentless sun. The social cost was woven into every mile, a reminder that the unity and efficiency enjoyed by some were built upon the compelled labor of many. The environmental footprint of these projects was equally transformative and rarely gentle. To build a road straight meant removing whatever stood in its way. Vast tracts of forest were cleared, not only for the roadbed itself, but to provide timber for bridges, way stations, and the endless fires of construction camps. Quarries were opened in hillsides, scouring the landscape to extract the durable stone needed for paving. Perhaps most significantly, the very hydrology of a region could be permanently altered. By digging deep drainage ditches and building elevated causeways, engineers redirected the natural flow of water. What ensured a dry road for travelers could inadvertently flood nearby fields or starve downstream ecosystems, demonstrating that human geometry, once imposed, created a new and sometimes unforgiving relationship with the land. This complex legacy holds a powerful duality. There is no question that these integrated networks spurred remarkable economic and cultural exchange. Ideas, religions, art, and technology flowed along these routes with traders and travelers, weaving together disparate regions into a shared tapestry of civilization. A pottery style from one province could appear in a market 1,000 miles away, and philosophical concepts could travel from academy to academy. This was the road as a conduit for connection, fostering a cosmopolitan world where a merchant from Syria might do business in Britain. Yet the very same road that carried olive oil and silk also carried the legions. It enabled not just trade but conquest, allowing armies to move with unprecedented speed to subdue rebellious territories or expand imperial borders. The road was a two-edged sword, a tool for cultural flowering that was also an instrument of domination, facilitating both the peaceful exchange of goods and the forceful imposition of a single law, language, and set of gods. To walk an ancient road today, then, is to tread upon a palimpsest of human experience. You are following a line of commerce and curiosity, but also one of ambition and authority. The straight path represents a monumental achievement of collective will and technical skill, a testament to what societies can build. Yet it also asks us to remember the full scope of that endeavor, to acknowledge the layers of social and environmental cost embedded in its stones. This honest perspective does not diminish the engineering marvel, it deepens our understanding of history itself. It reveals ancient empires not as monolithic forces of good or ill, but as complex human systems that could create breathtaking beauty and foster connection, while simultaneously relying on systems of control and extraction. The road itself is neutral, a geometry of efficiency. It is the purposes to which it was put and the means by which it was built that contain the full, challenging story of our past. This legacy is not a simple one, but in its contradictions, it mirrors the enduring complexity of human civilization itself, forever striving to bridge the distance between ambition and its cost. So step away from the satellite imagery and the modern maps for a moment. Place yourself in an open field, tasked with a simple directive to mark a perfectly straight line from one side to the other. You have no laser levels, no theodolite, just your own eyes, some wooden stakes, and a length of rope. How would you begin? This very exercise strips away the mystery and connects us directly to the ancient surveyor's mindset. Your first instinct would be to find something fixed and reliable to aim for. You might pick a distinctive tree on the far tree line or a rock on a distant hill. Without realizing it, you have just chosen your own personal North Star, a stable reference point to guide your entire effort. This is the foundational act, the translation of a distant, permanent marker into a local direction. With your endpoints chosen, you would then walk to your starting position, drive in your first stake, and look toward that distant tree. Now comes the true test of alignment. You would ask a friend to walk out 100 paces and plant a second stake. From your fixed position, you would squint, point, and give instructions. Move it left a little, now back to the right, stop. You are commanding them until that second stake disappears from your view, perfectly hidden behind the first. In that moment, you have not just placed a piece of wood, you have created a straight line segment using nothing but human vision and communication. You would then walk to that second stake, become the new anchor, and repeat the process with a third stake further on. Leapfrogging forward, you would slowly, painstakingly march that line of sight across the entire field. This is the ancient method of ranging, made immediate and personal. It feels simple, almost obvious, until you try it on a breezy day, with your friend misunderstanding a hand signal, or with your own eye straining to judge true alignment over a long distance. You quickly learn that precision is a fragile agreement between people and the elements. Now, what about making sure your path doesn't slope into a ditch? For that, you might use a trick as old as civilization itself. Take a long, transparent garden hose, fill it with water, and hold both ends up. The water, seeking its own level, will settle at exactly the same height in each end. By marking that height on a stake at one end, you can walk to the other and see if the ground is higher or lower, allowing you to trace a consistent, gentle grade. This is the principle of the connected vessel, a direct ancestor of the Roman chorobates. This simple thought experiment does something remarkable. It demystifies the monumental. It reveals that the core genius of ancient surveying was not in possessing secret knowledge, but in the rigorous, systematic application of fundamental principles anyone can observe. It was about turning the basic truths of geometry and physics into a repeatable physical process. The distance from your backyard experiment to the Via Appia is not one of kind, but of sheer scale, coordination, and the unwavering will to see that straight line continue, not just across a field, but across an entire continent. The methods were accessible, rooted in a deep understanding of the natural world. The true magic was in the monumental patience and organization that turned those simple ideas into the bones of empires. That simple act of drawing a line in a field reveals a profound truth about ourselves. On a deeper level, the act of creating a straight road represents a fundamental human desire to impose order, predictability, and rationality onto a seemingly chaotic natural world. It is an act of optimism and will. Think of the landscape before the surveyor arrives, a place governed by ancient, meandering streams, thickets that grow where they please, and hills that rise and fall without any pattern we can easily comprehend. It is beautiful, but it is not built for human purpose. The straight road is a declaration against that randomness. It says we will not be subject to the winding ways of animal trails or the capricious course of a river. We will decide the most efficient path, and we will make the land conform to our logic. This is not just engineering, it is philosophy made visible. The road is a line of intention, a physical manifestation of the belief that a destination can be reached by the most direct means, that progress is not only possible but can be measured and guaranteed. Every stone laid is a vote of confidence in the future, a bet that the travelers who come next will share the same destination and will benefit from this cleared, defined way forward. This philosophical drive connects the Roman engineer to the modern city planner laying out a grid of streets, and even to our personal lives, where we constantly seek to straighten our own paths toward our goals. We create schedules which are straight lines through time. We set budgets, straight lines through our finances. We follow step-by-step plans for education or career advancement, all in an effort to minimize the wandering, to reduce the unpredictable detours of life. We are using the tools and knowledge available to us, whether it is a calendar app or a mentor's advice, to do what the Agrimensor did with his Groma, to establish a reliable bearing and then move steadily toward a chosen point on the horizon. The ancient road, therefore, is more than a relic, it is a mirror. It reflects our enduring need to make sense of our surroundings, to replace uncertainty with a plan, and to believe that with careful measurement and determined effort, we can indeed forge a direct route from where we are to where we wish to be. That line across the land is ultimately a line of hope, etched not just in stone, but in the very character of human ambition. The stones beneath our feet now hold a different kind of power. These ancient roads, once the vital arteries of empires, have been repurposed by time. Today, we encounter them not as bustling highways, but as quiet archaeological treasures, scenic hiking trails, or simply faint lines etched across a farmer's field from an airplane window. This shift in perspective is profound. We no longer see them purely as feats of infrastructure, but as monuments to human perseverance, as cultural heritage that belongs to all of humanity. Their value has transformed from the functional to the symbolic, from moving armies to moving the human spirit. Yet this very status as a cherished relic brings with it a new and constant challenge, the quiet battle for their preservation. The same landscapes they once conquered now threaten to reclaim them or erase them entirely. Modern agriculture, with its deep plowing and land consolidation, can unknowingly obliterate a buried roadbed. Urban development and new construction projects often pave over history without a second thought. Even the gentle, relentless work of time, through erosion and root growth, continues to wear away at what remains. These roads, built to last forever, now exist in a fragile equilibrium caught between memory and oblivion. Recognizing this, dedicated organizations and archaeologists around the world have taken up the role of guardians. Their work is a blend of old-fashioned fieldwork and cutting-edge technology. Teams walk the suspected routes, looking for the subtle rise of an agger, the raised foundation, or the scatter of ancient paving stones in a plowed field. But their most powerful tool now looks down from space. Satellite imagery and aerial LiDAR scans allow researchers to see what the naked eye cannot, revealing the ghostly imprint of a road beneath a dense forest canopy, or tracing its straight path across modern farmland, showing the full, breathtaking extent of networks that have been fragmented for centuries. This digital mapping is more than just cartography. It is an act of recovery, piecing together a scattered skeleton to understand the complete organism of an ancient transportation system. When you have the privilege to walk a surviving stretch like the Via Appia Antica outside Rome, the experience transcends a simple hike. You are not just on a path, you are on a timeline. Your boots scuff against stones worn smooth by millions of footsteps, by the sandals of legionnaires marching to war, the sandals of merchants hauling spices, the hooves of imperial messengers' horses. You are literally tracing the groove cut by history, a physical connection to the minds that measured this line and the hands that laid it. This tangible link is what transforms dry history into felt experience. It shifts our modern gaze from one of mere academic interest to one of deep, personal resonance. We stop seeing just a road and start seeing a story of ambition, of collective effort, of a civilization's reach etched directly into the planet. To walk it is to understand in your bones that the straight line is not just a geometric fact, but a lasting echo of human will, a whisper from the past that still very clearly points the way. The story of these ancient straight lines is, in the end, a testament to the power of the human eye and mind. From celestial observations to the humble sighting pole, this journey reveals a profound lesson in resourcefulness. We have traced the path from the strategic demands of empire to the precise geometry of the Groma, from the enduring stones of the Via Appia to the breathtaking stairways of the Inca. What emerges is a legacy built not on secret technology, but on universal principles, meticulous observation, foundational mathematics, and sheer, unwavering determination. These roads were always more than stone and gravel. They were the physical expression of a deep human craving for order, a bold statement of ambition, and a tangible lifeline of connection. They transformed wilderness into a network, distance into a measured journey, and isolation into community. Today, as we navigate our world with satellites and digital precision, it is worth remembering this foundational ingenuity. The straight line first charted across a continent was a triumph of vision, a vision that saw possibility in a blank horizon, and then possessed the patience to make it real with simple tools and methodical effort. That combination of a clear goal and the disciplined steps to achieve it literally paved the way for history. It reminds us that the most enduring monuments often begin not with complex machinery, but with a single stake driven into the ground, a sighting taken toward a distant star, and the collective will to follow that line one measured step at a time. If this exploration of ancient genius resonated with you, we would love to hear your thoughts. Which civilization's engineering feats, from the Roman aqueducts to the Inca mountain trails, most inspire your sense of wonder? Share your reflections in the comments below, and subscribe for more journeys into the enduring mysteries of our shared